Hi guys, Stupid Simple here, where I take topics that make me feel stupid and try and make them simple. Today I'll be talking about differentiation and more specifically the product rule. So, from my last video on this topic, we covered the chain rule. So if you haven't seen that yet, or you would like a recap of how to do that method, I'd recommend checking out the video on it. You'll find it in the playlist and hopefully link below. And if you're comfortable with differentiation as a whole, i.e. in using, say, the power rule, then brilliant, you'll be ready for this lesson as well. But if you're not comfortable with differentiating things relatively quickly, i.e. seeing that x to the power of 5 differentiates to 5x to the 4, then perhaps check out the video on that as well, which I'll also link below. But in the meantime, today we will be covering the product rule. So as I reiterated in the chain rule video, there is a slight difference between the two, the chain rule and the product rule, that make them seem similar in theory, but really different in practice. And that is mostly that for the chain rule, you will have some function f, which is acting on some function g of x, or whatever variable you're using. So that is defining when to use the chain rule. However, for the product rule, we will expect to see some function f, in this case in x, multiplying with some function g, again in x. So this is when we will be using the product rule. They look similar here. Well, no, they look very different here, but they can get a little bit confusing when you have a lot of x's swimming around in a lot of different terms, and it's kind of difficult to see what to use when. We covered the application of chain rule last time, where we could see when something acts on something else, how to deal with that. And today, we'll cover what to do when two things are multiplied together. So I think the easiest way to get started here is just to look at an example. Oops. So, if we go across, say we had f of x be a function f, and let's call that x squared. And let's say we have some other function g of x, which equals cos of x. We can then define, using the two of them together, some function x squared cos of x. And let's just call that h. Just another letter randomly. We can see that we have one function, x squared, multiplied by another function, cos of x. Equally, we do not have, it's not the same as, cos of x squared, which technically does have both terms in. This is a multiplication, and therefore we can use the product rule. This is a composite, and therefore would involve the chain rule. We've covered how to do the chain rule, so today we'll be focusing entirely on the product rule. So, what is the product rule? Well, I'll lay out a formal definition here, and then we'll see how to apply that to this case. So if we want to differentiate or find d by dx of some function f of x, let's use the color coding for obvious sake, of f of x times by some function g of x, then we want to find f of x multiplied by g prime of x plus f prime of x, let's move over just a little bit, multiplied by g of x. And that's all there is to it. So we have an f multiplying a g, or any two functions multiplying each other. Our first function gets thrown to the front, and then its derivative gets put here. For the first f that didn't get differentiated, our g does get differentiated and multiplied with it. And for the f that is differentiated, it gets the non-differentiated g. So we end up with two terms involving one non-differentiated, and one differentiated, and one differentiated, and one non-differentiated. I hope that makes sense. Just look at it for a few seconds if that helps, and see that you have two originals of each and each of their differentials. So if we're looking to find, let's keep that on screen for a sec. So if we are looking to find h prime of x, which is to say the differential of this equation, then we're going to want to do two things which we have done standard in the last few equations, which is first to find f prime of x, and also to find g prime of x. So to start, since f of x equals x squared, f prime of x therefore equals 2x. And since g of x is cos of x, we therefore know that g prime of x equals minus sin of x, or minus sine of x, depending how you pronounce it. With these, we can substitute straight into our equation. So first things first, f of x, which is x squared. So that goes there. We then multiply by our g prime, which is right here. So we'll go zoop, and throw in a minus sine of x. I put the brackets here and here just to delineate that the minus is a multiplication, and this is not x squared minus sine x, but rather x squared times minus sine x, which we'll need to know in a second. We'll then add the next term in our big equation, which is f prime, which we can find up top here, and that's going to come right down to the bottom, which as we can see is 2x. And we'll do exactly the same so far, and we multiply by our g of x, which we can find right here as cos of x. So that's going to come all the way down here. Okay, and from there, all we're going to do is simplify things a little bit. Because this term is a minus, I'm actually going to throw it over to the right-hand side, and because this term is positive, I'm going to put it to the left, just for making things a bit easier to read. So therefore we have 2x cos of x minus x squared sine of x. And that's it. That's everything. We have now differentiated a product of functions, hence the name product rule. We'll do a few more examples and run through this, and hopefully this will make a bit more sense, but let's keep going. So let's consider now the function again, h of x equals f of x multiplied by g of x, where in this case we have f of x equals, let's say, e to the x. I try and choose different terms for my equations as I go through, so you can see some specific examples as well. But I do intend to do a full video on the more specific differentiations, be that trigonometry, be that e, be that ln, or other such things that may not be so obvious to differentiate immediately. But besides, f of x is e of x, and g of x equals, let's say, 2x to the power of 6. If we're looking for h of x, firstly, we're going to need to find f prime of x. If we apply the power rule, we see that e to the x takes its power down from the top and becomes x e to the x minus 1. But because we're multiplying e by x and it's to the power of x, the x coefficient becomes absorbed again into the power system and it deletes the minus 1. And so we're left with the rather nice result that the differentiation of e to the x is simply e to the x. We then do the same for g of x, where we find g prime of x, which equals, if we take the power from 6 down to 2, we have 12 x, and we have 6 minus 1, it's 5. And that's all we need to do. And then again, we apply the rule that h prime of x is f of x multiplied by g prime of x plus f prime of x multiplied by g of x. A little dash there. I should specify as well that the order of these two terms does not matter. As you saw in the last example, I flipped them over at the end because having a plus minus something is to me, feels a lot nicer than reading minus something plus something. It's personal preference. The order doesn't matter since they're being added together anyway. But this is just how I'm going to set this out now so that we can have some consistency in notation. So let's do exactly that. Let's find h prime of x. First thing we're going to do is find our f of x here, which is e to the x, and we'll bring that down to the front, which is going to go straight there. Next thing we'll do is add our g prime of x, which is right here, our 12x to the 5th. So we'll throw that multiplying the e to the x. And then we'll add the other half, which is to say we start with our f prime of x, which as we found out before is just e to the x as well. So even though it's a different term, f and f prime, they still both equal e to the x. So that's fine. And then we'll multiply by our g of x, which was back here at the start, 2x to the 6th power. And there we are, we're done. You could rearrange the terms around so that the 12x to the 5th multiply the e's to the x, but that's kind of personal preference. We could also arguably factorize and say we have e to the x 12x to the 5th plus 2x to the 6th, which is to say 2e to the x of 6 x to the 5th plus x to the 6th, which is equivalent to 2x to the 5th e to the x 6 plus x. But all of these are valid. As far as I'm concerned, this is correct, this is correct, this is correct, and this is correct. They're all just rearranges of one another, depending on how you want to lay out your answers. So let's have a look at something that might be an easy pitfall, something that might make you think, easy, product rule, let's go, I'm done. Life is simple, because it's a relatively easy formula to follow. Let's say we're looking for h of x, if I can draw letters at all, h of x, which equals some function f of x times by some function g of x, and then we call our functions f of x equals x cubed and g of x equals 5x to the 10th power, shall we say. Because we're doing power rule, you may be inclined to think, okay, well, the first step, as per usual, is to find f prime of x, which is 3x squared, and g prime, which equals 50x to the 9th, and then apply the formula as is. But if you look a little bit closely, you'll see that we defined h of x to be f times g. And these terms, which are f and g, x cubed and 5x to the 10th, they do multiply. If you know index multiplication tool, you know that x to the n times x to the m equals x to the n plus m. And since we have x to the power of n times m, we also have 5 times x to the power of 10 plus up top, 3, which is equal to 5x to the 13th, which we can apply the usual power rule to. So therefore it will differentiate into 5 times 13, which is 65x to the 12th. Let's double check if this applies with the power rule. So we'll do exactly the same as before. We will do our h prime of x equals f prime, as we saw before, let's do it with blue, is 3x squared. G of x is 5x to the 10th. And then we're going to add f, which is x cubed, and g prime of x, which is 50x to the 9th. If we simplify these terms, let's do it in black, 3 times 5 is 15, and 2 plus 10 is 12. So this becomes 15x to the 12th. And here we have 1 times 50, sneaky 1 in front of the x cubed, is 50. And 3 plus 9 is also 12. If we add them together, we do indeed still get 65x to the 12th. So the methods work both ways. But depending on how comfortable you are with notation, with multiplication, or with applying the power rule, simple differentiation, you'll see that we had to do 2 extra differentiations to apply the power rule. And we also then had to compute a few extra multiplications and power multiplications to get the same result. Both methods are valid, and you have no reason to concern yourself if you use one or the other, but it is useful to note that looking at the question first and considering what it's asking you, and even if it doesn't objectively define what h of x is, or whatever the total function you're differentiating is, like I didn't write here, if you look at it and write down what you're actually being asked to do in a case like this, you will find that it might be easier to take a different route, or there might be a simpler route than just following a long equation. So that's a relatively easy pitfall to come across. I'd say the other biggest pitfall that you're likely to find is applying the chain rule, or potentially even the quotient rule, which will be next video, in the case where the product rule would be valid. Either way, we'll do another example of some slightly harder values, and then we'll call it there. So for now, let's move over and do another one. Let's define h of x as f of x multiplied by some function g of x, where we have f of x equals ln, or ln, of x. If you're not familiar with this, don't worry. We'll cover it in a separate video as well. And where we have g of x equals, let's say, the square root of x. We've used it a few times now, but it's useful for showing that indices can look squarey but aren't. First things first, we can see that if we multiply these two things together, they don't commute like the last equation did, so we are indeed going to be using the product rule and not the power rule or some other thing. Granted, if you have an easier method that works, feel free to tell me. I'd be interested to know. In the meantime, we'll start with our usual f prime of x. And if you differentiate ln of x, you will be given 1 divided by x. The specifics of that I'll go into detail in a separate video, along with e to the x and trigonometry and all those other fun ones that we come across. But for now, we'll remind ourselves that g prime of x equals, if it's hard to remember, you can always rewrite x, square root of x as x to the power of a half and apply the power rule. So g prime of x is 1/2 x to the minus 1/2. Brilliant. Now let's try our h prime of x and throw in our values. So first things first, we're going to use, if you remember it from a couple screens ago, f times g prime. But again, the order doesn't exactly matter. I'm just trying to keep things consistent for the sake of explanation. But for now, we will take our blue and substitute f, which in this case is ln of x, and multiply it by our g prime, which is 1/2 x to the power of minus 1/2. We'll then add our other parts, so we'll then add our square root of x, our g, multiplied by f prime, which in this case is 1 divided by x. And then from there we're going to simplify, or rearrange as best we can, which would be 1/2 x to the minus 1/2. I'm going to choose to keep that in index form because it looks a bit messy with surds and other square roots on the bottom side. But we're going to multiply that by ln of x and consider the 1/2 x to the minus 1/2 as a coefficient of ln. And we're going to add that to the square root of x divided by x. So that's the product rule. It's a useful differentiation tool in order to differentiate products, hence the name. It's slightly easier, I would imagine, than using the chain rule, even though there is one more term in it. If you remember, the chain rule was f prime of g of x and g prime of x. In this case, however, which was 3 things. In this case, however, we're using f, g, f prime, and g prime, so 4 terms. Although I find that we don't have to submit g into the f prime, makes the computations here a little bit easier and a little bit less likely to have human error mistakes. Regardless, the best way to avoid those as a whole is practice, and I recommend you make as many examples of this in your head as you'd like and give them a go. I intend to do a long video in a few videos' time, going over as many examples as I can think of these questions, ranging from relatively simple examples like we've done here to stuff that is just more complicated than you should reasonably see, but you'll still be prepared in case something that you weren't expecting comes up, using strictly the tools I've given here. In the meantime, though, that's the product rule. I hope you've learned something, and if not, give me a comment, tell me. If there's something that I've said here that doesn't make a lot of sense and you don't fully understand or want me to explain further in detail, please tell me. And if there are any other specific topics unrelated to this but still vaguely in the math scene, tell me. I'd love to know. I'll be glad to do a full dedicated video on them. In the meantime, so thank you very much for watching. I've been Stupid Simple, and I hope you found that simple. Right?